Hello everyone, welcome back to our YouTube channel Becoming a ROS Developer. I'm Desire and today we've got Matthew who has completed the course Linux Basics for Robotics and he will be giving us a presentation on that. So what I'm going to do is I'm going to hand over the platform to him and then he can begin his presentation. Okay Matthew,
Right.
whenever you're ready.
Mm-hmm. I'm ready. Okay, perfect. So first thing I want to demonstrate, obviously, is the live demonstration
Mm-hmm.
of the project itself. So let me connect to the robot.
Okay.
Uh-huh. I thought I selected a time.
So you have that booking, right?
Yeah.
Okay, so
Oh wait,
that
right here.
means yeah, that
Right here.
means
There we
it's
go.
okay. Yeah, that means it's
Hmm.
yours. That's why it's busy.
Yeah. Yeah, of course.
All right.
So yeah, the demonstration obviously for today is to demonstrate the obstacle avoider bash that we made.
Mm-hmm.
So first thing I'm going to connect to is the actual interface so we can actually get connected to the robot on the terminal right here. And then on the second terminal, it's actually running the bash file.
Mm-hmm.
Let's do that right here. All right, perfect.
Mm-hmm.
Now, as we can see, the actual file is running, and we can see the entire thing working properly. But since it's obviously in a corner, it's going to take a while to get out of there.
Mm-hmm. Okay.
There we go. That happened to me last time too. It was right next to the wall, so it kept turning right and left.
Yeah, yeah. These oscillations do
Mhm,
happen, so that's if you
mhm.
don't guard against them. So there should be a way to do that.
Yeah.
Not that
Hmm.
we expect you to do it in this project, but it presents
Yeah.
obstacles. Yeah.
Yeah. I think in this moment it's actually stuck.
Okay, let's get it out of that zone. Maybe use tailor over the joystick and
Yeah.
just move it out.
Let's use the joystick for a second over here. All right, let's move it a little bit forward. Just let it move a little forward, forward. There we go. I think after this one, after it turns left again, it can start moving on its own now.
Mm-hmm.
Mhm. Let's see, it's probably gonna move forward now. There we go. Perfect.
Is the statistics script running?
Yeah. Oh, the statistics. Oh, I forgot the statistics one. Let me open up the other terminal.
Yeah, no worries. Just have it running so that we can also um, see what it's publishing, what it's getting.
For sure. Of course. Let me do the slash. There we go. Perfect. And then we move this a little bit forward over here so we can see the entire thing.
Mm-hmm.
Mhm. So throughout this entire script, it's essentially what I found very interesting is when it would move forward. From last time that I discovered, something that I didn't see and saw that it was essential was actually implementing the threshold when it was moving forward to keep it at a at a safe distance every time it was moving forward.
Mm-hmm.
Because sometimes the robot itself wouldn't kind of like maintain that safe distance. So when I wouldn't activate the threshold, sometimes it would crash into certain objects.
Can you explain to me why you chose to
Mhm.
implement it as a condition? Like, why would you have the threshold is? something that can be checked true or false. Maybe I didn't get your explanation correctly, but from what you said, that's what I
Mm-hmm.
have a feeling might have been going on, or might have
Mm-hmm.
been the issue last time.
Yeah, of course. So the issue last time, what I was looking at is actually I forgot to actually initiate it the correct way. So I didn't have the dollar sign right next to the threshold over here, let's say over here. So it wasn't activating correctly.
Right.
That's what the issue was. But if you want, we could actually just go through this entire file directly and see why it's actually working and why the cases are properly made.
All right. Yeah, we
Mhm.
have seen it avoid obstacles, so that's quite good. Just so maybe
Mhm.
stop execution, and then we can go through that
Of
file,
course.
and
Mhm.
you can highlight some of the key notes as you've been saying.
Of course.
You don't have to disconnect. Oh, okay.
Oh.
No worries.
So sorry. Okay, perfect. So essentially the entire thing. So we first start, obviously, we put the angular and the linear commands at 0, so we can start from scratch. And then the threshold is basically a safety limit. So every time the robot scans in front of it, it gives the types of meters it has available to actually move,
Mm,
the types of meters it has free. So the threshold is basically giving it a limit for basically how how close can it actually be. So if it's lower than 0.3 meters, that means it's very close,
mm-hmm,
which gives us a detail basically saying we shouldn't move in this area because it's way too close. Let's try to check other areas that are actually a little bit more available.
okay.
So the way we actually check this is we start getting into our scans. So the left, the front right, and the right range basically has different types of scanners that we're going to be using in these different type of cases.
Did we mention
So
them?
we just I'll be introducing it right here, I think. Yeah.
All
So you have
right.
eight different cases.
I'm quite keen to know
hmm
why you did that. Nothing wrong, but
hmm
it's
Yeah.
interesting to see the logic behind it.
Yeah, yeah, yeah. So we have eight different cases, and these cases basically depend on just if they're free. So, like I said, the threshold, we're basically testing it against the threshold. So basically the variable is called free because we're testing if it's greater than the threshold. So if the scan is greater than the threshold, that means we have a free area to move into, depending on the scans of the other areas as well.
Okay.
So we start testing them, right? So let's go over here. So we start testing our first case, which is if the front left is not free and the front right is not free and the front is not free, then we just test which one actually has a better angle or which one has a better range, depending on the left range and the right range.
Mm,
So then we just test that out. And then if the left range is bigger than the right range, meaning we have more space to move into the left range, we move to the left. And if it's the opposite, then that's the else statement, then we move to the right. We turn to the right.
mm-hmm,
Mhm. And then it's the same thing here, but instead we're just different. We're doing a different case. So it's if the front left is not free, the front is not free, but now we have a difference. The front right is free. So we obviously identify that the front right is free, and then we basically turn to the right. And
okay.
then we have another case right here, which is our first move forward case, which basically identifies if the front left is not free, but the front is free and the front right isn't free, which meaning we have space to the front. So then we move forward, and the way we move forward is like I explained, we have the front range, and then we add like a safety parameter where we subtract the threshold.
Mm-hmm,
And then after we basically instantiate a fixed speed of how fast it's going to be moving. And this 1 second parameter setting delay is basically what identified it is the actual delay that it's going to have when it actually activates
mm-hmm.
on the actual platform itself.
Mm,
So,
okay.
mhm,
What? Okay, so there is no guarantee, right? There is no guarantee that that's the
yeah.
actual delay, right? So maybe I
hmm
might have gotten your explanation slightly wrong. So
hmm
I'm gonna say, can you give it a try one more time? What is the delay?
Yeah, of course. So the setting delay, I was imagining it was basically to because when you start running it on the actual platform, let's say Gizmo or with the actual robot itself,
Mm.
um it delays. It delays to actually like start like mhm,
Yeah, okay,
like
so
something in along those lines.
yeah, I think you're on the right path. Think of it as a guide,
Hmm.
right? It's not guaranteed that
Hmm.
we have a delay of 1 second. No. So I think you are thinking about it correctly. It's just maybe expressing it not so well, right? So the idea is that
Hmm.
you are trying to give your robot some safety measure, right? You're
Hmm.
saying in case you get to this point, right, before something kicks in, you want to allow for that time between the trigger calling the robot to stop and then the robot actually responding to that, right? So that's
Mm.
yeah. So that's the kind of work that your delay is doing in this case, right? So you do have a general idea of what it's doing. Maybe it's just the explanation that's not going as expected. But anyway, no worries. Let's go on.
Okay. Okay, perfect. So something I actually implemented that's very interesting is the special case. Because sometimes when I would actually test the robot itself, when it would have a very specific meter, when it would be right next to the wall, but the thing is, it was very close to it, but it was above 0 0.3 meters, which is the threshold. Sometimes it would be like 0 0.350 meter. And the thing is, sometimes when it would be 0 0.350 meters, it would then go through the entire formula. So it would be 0 0.350 minus 0 0.300, which would then be 0 0.05.
Mm-hmm.
And then it would do divided by 0 0.100. And then that would be zero point 0.5. And then zero point 0.5 minus 1.0 because of the parameter setting delay. And
Mm-hmm.
it would actually give you a negative number.
Mm-hmm.
And with that negative number, sometimes it would the sleep command would actually give me an error saying that a negative number has been implemented because of what the formulas here were basically signifying.
Okay.
So the if statement I basically implemented was to actually check if a negative number was actually printed from this range. If a negative number was printed, it would just continue with the other if like the else if statements. But if a negative number wasn't printed, that meaning there is a lot of space to actually move, it would just go like normal. So then I wouldn't allow for small little movements to actually happen,
Mm,
but
okay.
rather just skip that small movement and just keep going forward by turning left or right.
Yeah. Okay. Okay. Yeah. Because I was going to ask. Okay, why did you not implemented a default mechanism where
Hmm.
it you try to do something in that direction, right? But it's pointless because it's
Hmm.
just going to move very little. So yeah,
Yeah.
that's a good approach, I think.
Hmm. So then we go to the other cases where the front left is not free, the front right is free, and the front is free.
Mm-hmm.
So we obviously turn right, and then we turn right, but a very slow right. So it's a very good case if you're very kind of like stuck in an area. So it turns right very slowly instead of turning a hard right, which is over here.
Mm-hmm. And can you explain to
So
me?
then,
So
mhm,
let's go back to that point when you say it turns slowly instead of a hard right. What are
mhm.
you doing exactly to the parameters, angular and linear velocities? Are you just manipulating angular velocity alone, or?
Yeah, basically the angular velocity is the only thing that I'm manipulating.
Okay.
So if you see over here, the angular velocity, it's like 0.942477, which obviously it turns a little bit faster,
I see.
but we have the same sleep. We have the same sleep number.
Okay.
But obviously the difference here is it's turning a little bit slower.
Okay, but for the same sleep time. Okay, I see.
Hmm.
Okay, let's go.
Yeah, of course. And then the front left, this time is free. The front is not free, and then the front right is not free, meaning obviously let's turn to the left, which is the same idea. We're returning to the left a little bit slower, so we can kind of like calculate that angle a little bit better.
Okay.
And we have the same sleep schedule. And then over here, we have basically kind of the same thing. So front left is free, the front right is not free, but the front the front isn't free, but the front right is free, then we basically choose the better side.
Mm-hmm. Yeah.
So we basically do the same calculation we did earlier. And let's see if the left range is greater than the right range, meaning that there's more space on the left. So if that condition is true, then we turn to the left. If the condition is not true, then we go to the else statement and we turn to the right
Mm-hmm.
with the same sleep schedule. And then we just reset it to zero right after.
Mm. Okay. All right. So it's
Hmm.
basically the same stuff that you're repeating for every case, right? Just changing
Hmm.
the different um, true and false values, right?
Yes, of course.
Okay. So here is
Hmm.
maybe a bit more global question, right? So
Hmm.
I understand you took five indexes, right, which gives you
Hmm.
the eight cases that we're talking about, right?
Hmm.
So with that in mind, um, what would be the limitation for you to consider more than five, right? So I just want to think about this globally, right? Given this
Hmm.
project and how you have been working with it, what is your limitation for not being able to go beyond five indexes, for example,
A limitation to go beyond five
or even
indexes.
to have more than
Okay.
eight cases?
Okay. So you're asking the question of why is it only eight cases? Why, like, what's the limit of only maintaining it eight cases?
Mm-hmm. Yeah.
Or, uh-huh.
Given the
Okay,
information
perfect.
given in the Roster Act, right? I want to understand from your
Hmm.
perspective what is that limit?
I think the limit basically is just the amount of like ranges we have that we can actually assess. So if like I imagine if there is more type of ranges that we can access, let's say if it's not only just assessing the right, the left, the front right, the front right, the front left, and then the front, if maybe we can assess a range that can be like backwards. So like the robot can scan behind itself, we can then assess, hey, maybe the front isn't accessible
Mm.
and the let's say it's pointing at a corner where obviously the front is accessible, the left is pretty like small, the right is pretty small. So if there's a lidar range that can assess the behind of the robot, then it can do a 360.
Mm-hmm.
It can do like a 180 and turn to the back of itself and then turn and go forward.
All right, I'm quite sure there is that option, right?
Oh,
Because
okay.
so the lidar scan data that you're receiving has got all that or the whole 360-degree view covered, right? But
Hmm.
let's restrict my question to the first five in the front. So basically, to
Hmm.
rephrase it, the question is saying what stops you from having a finer resolution beyond eight cases? So why not 16 in the front alone, right? And which scale is
Mm.
limiting you? Remember, I'm asking within the context of this project, right? I'm not,
Yeah.
yeah,
I guess like something that's limiting me is hmm.
it's a script that you're actually working with.
Yeah, yeah, yeah. So with the same indexes that we have, I guess what would be limiting me was mhm,
Let me give you a guide.
front
Remember,
left.
you're using functions, right? You have got functions that you're
Hmm.
given that
Yeah.
pull out LiDAR scan index data from the robot interface.py, right?
Uh-huh.
Yeah. So let's think
Yeah.
about it in the context of that of that file.
Hmm. So something I kind of like understood is just maybe I could have used the left ranges and the right ranges a little bit more inside of the cases itself because through the cases I'm assessing that I only use front left and the front right in the front. Is that kind of like where we're heading? Like a question, like because that's kind of like what I understood a little bit.
Yeah, no, not really. Anyway, so I'll give you guide. I wanted you to think about it beyond a
Hmm.
little bit of what you had to do, right? So
Hmm.
so the cases that you are considering, right? The front left,
Hmm.
left and right, right?
Hmm.
The the way you're working with them is that there is a global assumption that our LiDAR scan data is being split into sectors, right? And
Hmm.
the more sectors we have, the better the resolution of our decision making, for example, in the case that you've got right now, right?
Mm-hmm.
So it can be pointless to have like um, more than 8 sectors, or more than, let's just say, 8 sectors, right? So that
Mm-hmm.
means for our indexes would have 5 in this case for the front, and then maybe 5 for the rear, right? Depends
Mm-hmm.
on the number of sectors that you've got. Like, you should get around that value, right? But what if you wanted 16? What would it mean for your ranges, right? It would mean that the ranges that you're considering, or the angle that each sector occupies, is gone down to half of that, right? So
Okay.
my question was, based on the information that you're getting, right? The answer that I was expecting was that your limitation would be the sectors that you are being given from the interface.py, right? The sectors that you are
Mm-hmm.
being given as a representative of the indexes for front left, front right, and then front, right? Because if that
Mm-hmm.
script doesn't give you more than 8 cases for the front, for example, you cannot have your obstacle avoider or bash use a resolution beyond that, right? So that's why I
Of
was saying
course.
it's a global question. You
Mm-hmm.
did make an attempt to go in the direction that I wanted, but it didn't come out the way I expected. But anyway, very, very well
Mm-hmm.
done. I think you show that you understand your implementation, and the
Mm-hmm.
way, the logic behind the decisions you have to make, which is part of the goal of this. And I'd like to say thank you, and a job well done, Matthew. So what we're gonna do is we're gonna wrap it up
Mm-hmm.
here, and then we'll finish our conversation on Zoom. All right?
Of course. Perfect. Mm-hmm.
All right, everyone. This was Matthew's presentation, and I'd like to encourage all those of you who would want to try this course, Linux Basics for Robotics, to go and do so. It's free. You can try it, and you can also come and have your project evaluated. So until next time, keep pushing your ROS learning. Bye bye.